Next, we'll talk about an application where we'll look more at inference and regression. So let's go back to the chicken data. Remember, we looked at ingesting lysine into chickens and then measuring how much weight they gained after a certain period of time. And so you can see we have a slightly increasing positive line here. The more lysine that a chicken ingests, the more they gain weight. And so we conducted a simple linear regression and found the slope of the line to be 35.8 and the intercept to be 12.5. And so we could go back and we can make predictions if we wanted to based on this regression formula. We could calculate all those formulas out by hand. That is, we would calculate the total sums of squares, we would calculate the regression sums of squares, and we would calculate the residual sums of squares. And so if we did that for all of the data that we have for the chicken and lysine, we would come out with these values for the total sums of squares, regression sums of squares, and residual sums of squares. Now what about sigma squared? This is the variance term. We could calculate this by dividing the residual sums of squares by its degrees of freedom. And so we would get then what we call the residual mean square. The residual mean square is calculated by the sums of squares for the residuals divided by n minus 2. And n minus 2 is the degrees of freedom for a regression. And it's n minus 2 because we've already estimated two things about this regression, beta 0 and beta 1. You can think about the residual mean square value as the measure of bounce around the fitted line. So then if we plug this in for the chicken and lysine equation, we would get a residual mean square of 1.0692. And so don't worry, we're going to have a handy way to calculate this or to keep track of all these calculations when we talk about the analysis of variance table. But going back to that residual mean square, it's only really meaningful for our calculations. What can we think about the units are for the chicken and lysine data? Well, it's in grams for is what we really want. So the residual mean square is actually in grams squared, but if we take the square root of it, we get the residual standard error, and that would be in grams, in this case for a chicken. So this is the output that R provides, and it's really more meaningful. The residual standard error you'll see in the R output, and this is really the best measure of the bounce around the regression line that R provides. So we can also do t-tests for the regression coefficients. And so these will test the hypothesis that the beta 1 value is 0. And then we could use these test statistics, depending on if we were looking at the slope, beta 1 hat, or we were looking at the intercept, beta 0 hat. And so because this is a t-test, we could use the t distribution and the t table to look at where these values fall. Each is a t random variable with n minus 2 degrees of freedom. The ultimate goal is to find out whether or not beta 1 hat is different from 0, and maybe whether or not beta 0 hat is different from 0. But we can also test whether they're different from some other value than 0. And so we could place that in the numerator by whatever value we're interested in. Say we might want to test whether or not beta 1 hat is different from 1 or 10 or 100. We could really put anything in there when we do the hypothesis test. And so we could ask the question, are beta 0 hat and beta 1 hat any good for the chicken and lysine data? And so we could perform a test of the null hypothesis that says beta 1 equals 0 and beta 0 equals 0. And that will find out if the slope and the intercept differ from the value 0. And we can set a level of significance of our test at 0.05, a common level of significance for most of our statistical tests. And so we'll look at these data in R and begin to see some of the output.